So we have derived the following result for this particular reaction. The threshold energy ratio to its rest mass was 6. So in other words, we can also write this in terms of the Q value. Like this. Okay, so that's one scenario. Let's now consider exactly the same reaction, but with a minor twist. Assume now that we tried this in our lab. We had a stationary target shooting particles towards it to enable this reaction. But now we'd like to see what happens if we, instead of having one target at rest, have both targets moving. So we accelerate them towards each other. So we now shoot particles towards each other instead of shooting one particle towards something at rest. And assume that we do this in a fashion so that the momentum of the particles are the same. So this is the center of mass system. Our lab system is now the center of mass system as well. So we're doing the same experiment, but in a slightly different way. Now, I won't go through the calculations for this particular scenario. I'll leave that to a later date. But what you can show is that in this case, the threshold energies for enabling this reaction, in other words, the minimum kinetic energy for particle 1 and 2, since both are moving, is now simply mc squared. So what does this mean? Well, the available energy before the collision is the rest energy plus the kinetic energy. The rest energy is 2mc squared. We have two particles, each mc squared. The kinetic energy, at the threshold, is also 2mc squared, because each particle has kinetic energy mc squared. So the total available energy before the collision is 4mc squared, which is precisely the minimum energy required in order to produce all of these particles, having them at rest. So in other words, in this scenario, we are utilizing the available kinetic energy with maximum efficiency. We're converting all of the available kinetic energy to rest energy. So this gives us, energetically speaking, the most economical situation. It's the most efficient scenario. So we see here now that the threshold energy is just 1/2 of the Q value of the reaction. Whereas in our initial scenario, where we had one target at rest, threshold energy was 3 times the Q value of the reaction. So we have actually, just by changing our experimental setup, managed to lower the threshold energy here by a factor 6. And that's a pretty big gain, right? You want to minimize the amount of energy required to make this work. So having this in mind, it's perhaps not a big mystery why they at CERN accelerate particles towards each other in these large rings instead of firing them at stationary targets. It is precisely because that in the case where you accelerate them towards each other, you're able to maximize the efficiency at which you convert kinetic energy to rest energy, and thus minimize the costs, for instance, of accelerating the particles in the first place. So that's why you shoot them towards each other. That's much better than shooting something towards something at rest. But there's another important question that presents itself here, I feel, and that is, why is there such a large difference? Can we account somehow for this large difference in threshold energy? Why is it so much lower when you're accelerating towards each other compared to when you shoot at something at rest? Any ideas? Because it's a pretty big difference, right? It's a factor of 6.
In the case where you shoot at a stationary target, you have a net momentum that has to be conserved. While in the second case, the net momentum is 0.
Exactly. So you're right on the money. We need, in this case, where we fire something at a stationary target, to preserve momentum. It has to be conserved during the reaction. So inevitably, we need some of the initial energy to go into the conservation of momentum, so the final product has the momentum required to conserve it. Whereas in this case, we have no net momentum. So all the initial kinetic energy can be converted to rest energy. We don't need any excess kinetic energy to go into the momentum to satisfy the conservation law. So that is the fundamental reason for why we get such a low threshold energy in this case. Okay. So these two examples were meant to illustrate precisely this efficiency argument, or why it's beneficial to accelerate particles towards each other. Now, I would like to take one more example, which I think is, I really like this example because it illustrates so many important points. So, similarly to yesterday, I'll give you a task. You'll have 10 minutes to solve the following. So the task is as follows. We have a photon of energy epsilon, which collides with another photon at an angle theta. Find the minimum value of epsilon, in other words, the threshold energy that enables this collision to produce a pair of particles, each with a mass m. So let me just draw this for you. And say the photon is so you have one photon going here, another photon coming in here, hitting it at an angle theta. So what is the minimum value of epsilon that enables us to produce a pair of particles with mass m? Okay. Does anyone have a suggestion for final answer for the threshold energy? No suggestions? Okay, so I'll sketch one way that we can solve this problem, and you can see if you agree, and if you would like to complement the solution with something you would do differently or so. So, okay, we'll use again the standard tools of this four momentum conservation and invariance. So let's say this is photon 1 and photon 2. So we start by writing down the four momentum. P1, and we have to choose some kind of coordinate system, so let me choose Z and X, like this. So theta is the polar angle in a standard Cartesian or spherical coordinate system. Okay, so it has a component along the x-axis, no component along the z-axis, y-axis, and the following energy. So I've used here that the momentum of a photon is its energy divided on c. So there's a component in x direction, y direction, and the following energy. So that's photon 1. Photon 2 is moving along the z-axis in this particular frame. So we have the following for momentum. In other words, the total for momentum before the production of these particles looks like this. Okay, so this whole business of the photons hitting each other at an angle theta is a bit inconvenient, right? This is what makes the problem stick out a bit. So it would be convenient for us if we could find some more suitable coordinate system where all the motion involved was just along one axis. So we don't have to worry about this angle at which they hit each other. Now I can accomplish this simply by choosing an inertial system, a reference frame, where the momentum, the three first components of this total form momentum vector is along one axis. So I'm just rotating my system. But I have to be careful because I have to do this in a way so that the sort of pt squared is an invariant quantity. So let this be the z-axis, for instance. In that case, I have pt prime, the four momentum in that new system, like this. So the energy remains unchanged. I'm not performing any change to, I'm not changing to an inertial frame which is moving compared to my original one, in which case I couldn't leave this last coordinate unchanged. I'm just rotating it spatially. So I assume that I've rotated it so that the total combined three momentum of the photons is now directed along the z-axis. So the question is now, what is p photon in this system? how can we identify what p photon is?
Could we just set theta so that we achieve the last equation?
But in that case, you would have to choose theta equals 0, right? So that would be a special case of the photons just hitting each other rectilinearly. So we want them to hit the physical situation is that they do hit each other at an angle of theta. So we can't fix theta or choose it conveniently. It has some value. But what we can do is to use this invariance of the form momentum. This one squared has to be equal to this one squared because it has the same value in any inertial system. So in other words, well, for the energy part, it's no problem because that has the same value. So what it means is just that we need to choose p photons so that the magnitude of the 3 momentum is the same in both inertial systems. And the magnitude of this 3 momentum I can obtain just by squaring each of these components and then taking the square root. So I get 1 over c like this. So the total 3 momentum in this rotated system is given like this, so that the magnitude of the momentum is the same in both systems. I then have my invariance, Lorentz invariance. Okay, so in this reference system, we're only dealing with motion along one axis. So that's the first lesson learned. We found a convenient reference system where the motion only takes place along one axis. So that's pretty much as far as we can get concerning the before situation. Now we have to consider the after situation. So the question is now, what is the form momenta of these two particles at the threshold energy? Because that's what we're interested in. We want the energy of the photon, epsilon, that provides us with the threshold energy, the minimum energy required to produce these two particles. So let's write the form moment of the produced particles as P3 and P4, since we use P1 and P2 for the photons. Well, we have used the invariance of the square of the form momentum. We couldn't use conservation of form momentum vector here, because we changed inertial systems. And as I emphasized in the beginning of the previous lecture, the conservation of form momentum only holds as a function of time in the same inertial frame. So we used instead the invariance of the square of the form momentum vector in any inertial system. But if you want to write down the form momentum vectors of the produced particles in the same reference system, then we can use conservation of form momentum, right? Because it's the same coordinate system. So from this form, this is the total form momentum before the collision. We can immediately see what the form momentum of the particles should be. Oh, sorry. Should have this form. And then 1/2 here to give the energy. So P3 is one of the particles with mass m. It has an energy which is given by the square root of p squared plus m squared c squared, which follows from this general relation. And keep in mind that we're dividing this on c due to the Minkowski metric we have chosen. So I haven't specified this p. I'm just saying that it has some 3 momentum, but it has to be along the z-axis because we need to conserve 4 momentum. And since the total 4 momentum before the collision it looks like this, it only has component along the z-axis, while after the collision it also has to have a component only along the z-axis. So we don't specify p, but we know that it has to be there. And the energy of the particle with this momentum is then given from the following general relation. So that's one of the particles. So what's the form momentum of the second particle, described by P4 prime? So now we have to think back of the definition of threshold energy. So from the definition of the threshold energy, we know that it's the minimum energy required in order to have all the resulting particles at rest in the center of mass system. That was the definition. Now, obviously, we're not dealing with the center of mass system here because we have a finite momentum. But if they're supposed to be at rest in the center of mass system, what does that say about the momentum of the two particles?
It has to be as opposite of the P3 particle. So it's 0, 0 minus P.
But in that case, so you mean like this? Like this? Okay. So in that case, the total form momentum after the collision would have 0 momentum, 3 momentum. But that would violate the fact that we need a finite 3 momentum. But if we instead do like this, because if the two particles are moving with equal momentum, then in the center of mass system, they are at rest. Right? So they actually need to have equal momentum, not opposite, to be at rest in the center of mass system. And in this way, we can conserve the momentum required here. So we're now in the following situation. this is the form momentum before and after. We have this. So that's the second lesson learned. The form of the form momentum vectors depends on if we're considering the threshold energy or not. So we've explicitly made use of the fact that we're considering the threshold energy in order to write down this form, because this dictates what the momentum of the particles has to be. Because the threshold energy is defined as the energy which leaves the particles at rest in the center of mass system, and thus they have to have the same momentum here. So they can also conserve the momentum before and after. So first thing we did was to rotate the system to take place only along one axis. Second thing was that we used the definition of the threshold energy, and we have now obtained the form momentum vectors before and after in the same inertial system. Okay, so now it's just a matter of equating these two expressions. So we have, on the one hand, we get these two equations by matching the form momentum. Oh, c squared, sorry. And what we need to do then is to extract epsilon from these two equations to find the threshold energy. Because we've already, in deriving these equations, we've already made use of the condition required to have the threshold energy. So the epsilon that enters here must be the threshold energy. And what I can do is, for instance, I can subtract this equation from this one. Which should give me this, which I can rearrange to this. So this is the threshold energy of the photon in order to enable this pair production. So this could actually represent, for instance, the following reaction, just pair production by means of photons, like this. Okay, so let's, as always, when you find an expression, an equation for the final result, take a minute, sit back, and think, is this physically reasonable? Well, what happens when the energy of the second photon, which has energy E, what happens when E becomes very large? Well, epsilon becomes very small. Is this reasonable? Why?
Because then the particle with E would have a lot of kinetic energy, which we can convert to rest energy.
Precisely. So in that case, you don't need as much energy from the incoming photon, because this one already has a bunch of energy which you can use to provide the energy required to produce these particles, the rest mass. So that seems reasonable, that it should be inversely proportional to E. Okay, so that seems okay. Now what about the angle? Because it has a somewhat peculiar angular dependence. What happens if theta equals 0? Let me just check the time here. Well, it diverges, right? 1 minus 1. And we'll continue the discussion of this next lecture.